Polar worksheet, question number 1. Find the expression for the slope of the tangent line to the curve r equals 99 plus 5 sine theta. So, to find the slope, of course, we need dy over dx. But to get this, dy dx equals dy d theta over dx d theta. Now remember our two formulas, x equals r cosine theta and y equals r sine theta. So using this, we can get d theta of r sine theta over d theta of r cosine theta. Now by chain rule, we get the formula for the slope dy dx, which is r cosine theta plus r prime sine theta over negative r sine theta plus r prime cosine theta. So now, using our equation, r equals 99 plus 5 sine theta, we first derive it to get r prime, and r prime equals 5 cosine theta, and now we plug it into our formula. So the expression for dy dx would equal 99 plus 5 sine theta cosine theta plus 5 cosine theta sine theta all over negative 99 plus 5 sine theta plus 5 cosine theta. And here we have our expression for the slope of the tangent line to the polar curve r equals 99 plus 5 sine theta. Problem number 5. Assume that a particle is traveling on the curve r equals 5 cosine 3 theta. Find dr d theta at theta equals pi over 6 and 5 pi over 3, and state whether the particle is traveling towards or away from the origin. Justify your answer. So, first of all, we're given the equation r equals 5 cosine of 3 theta. Now we're asked to find dr d theta, so let's first derive it. So we have dr d theta equals negative 5 sine of 3 theta, and by chain rule we have another multiply or times 3 on the outside. So this equals negative 15 sine 3 theta. Okay, so that's our dr d theta. Now we're asked to find theta, dr d theta at those two theta values. So first, let's go dr d theta of pi over 6. So this would equal the negative 15 sine of 3 times pi over 6, which is equal to negative 15 sine pi over 2. And we know sine pi over 2 is 1, so this equals negative 15. Now it asks us to state whether the particle is moving towards or away from the origin. So since dr d theta equals negative 15 at pi over 6 is less than 0, the particle is traveling towards the origin. Okay, now we have r prime of 5 pi over 3. So this equals negative 15 sine of 3 times 5 pi over 3, and this equals negative 15 sine 5 pi. Now any multiple of pi with the sine function is 0, so this equals 0. So since dr d theta equals 0, the particle is not moving towards or away from the origin and is staying in place. Okay, now on to the next example problem. Number 8. Find the area of the region created by the polar curve r equals sine theta. Now first, let's just graph this so that we get a visual. So r equals sine theta starts at 0, 0. It has 0.10 up here, and it is a circle. So it's a circle with a diameter of 1. Okay, now that we have this region drawn, we want to find the area using polar integration. So we have the integral 1/2 the integral from 0 to pi of sine theta squared d theta. Now the bounds here are 0 to pi because the curve r equals sine theta repeats itself twice on the interval of 0 to 2 pi. Now if we put this as 2 pi, we would get double the area, and that's not what we want. So we put it as 0 to pi so that we don't get repeats. So evaluating this, we get 1/2 integral 0 to pi, and then using the power reducing formula, we get 1/2 1 minus cosine 2 theta d theta, and from this we get 1/2 0 to pi of 1/2 minus 1/2 cosine 2 theta d theta. Now taking the antiderivative, we get 1/2 of theta over 2 minus sine 2 theta 1/4 from 0 to pi. Okay, now plugging the values in, get 1/2 and then pi over 2 minus 0 minus 0 minus 0, and this equals pi over 4, and that is the area of the circle here. Now another smart way to approach this is to realize that, oh, this is just a circle with a diameter of 1, so therefore its radius is equal to 1/2, and we can just find it using the formula for area of a circle. So we have 1/2 squared times pi, which is also pi over 4ths. So whenever you have a geometrical shape such as a circle created by the polar curves, you can just use this shortcut and think of it as a circular geometric shape and use the formula for the area of a circle.
Number 9. Find the area in the area loop of the polar curve r equals 2 plus 4 sine theta. Here's the graph for that polar curve, and as you can see, that here's an inner loop that starts at the origin and ends at the origin. So what we want to find is the intersections between the polar curve and the origin. So we're going to set 0 equals 2 plus 4 sine theta. Using algebra, we can find out that sine theta needs to equal negative 1/2, where theta is going to be equal to 7 pi over 6 and 11 pi over 6. Next, to find the area of that inner loop, we're going to do, using the area formula, half times a to b, which is a is 7 pi over 6, b is 11 pi over 6 of r, which is 2 plus 4 sine theta, squared d theta. Using symmetry, we can eliminate this 1/2 by changing the bounds from 7 pi over 6 to 3 pi over 2, r squared d theta. Evaluating this integral, we can just distribute this squared. We're going to 4 plus 16 sine theta plus 16 sine squared theta d theta. Next, we're going to factor out a 4. So it's going to be 4 times the integral of 7 pi over 6 to 3 pi over 2 of 1 plus 4 sine theta plus 4 sine squared theta d theta. Next, using power reducing, we can substitute this for 2 times 1 minus cosine 2 theta. Okay? Next, we're going to add up like terms, which is going to be same bounds. So that's going to be 3 plus 4 sine theta minus 2 cosine 2 theta. Next, to evaluate integral, we're going to do 4 times 3 theta minus 4 cosine theta minus sine 2 theta from 7 pi over 6 to 3 pi over 2. So what we're going to do here is substitute 3 pi over 2 in. For this, that's going to be 9 pi over 2. It's 4 minus 3. Cosine of 3 pi over 2 is 0. It's minus 0. Sine of 3 pi, since there's a 2 coefficient there, will be also 0. Then minus, for the 7 pi over 6, minus 7 pi over 2. Cosine of 7 pi over 6 is negative 3 root 3 over 2, so it's going to be negative 2 root 3. Then, last thing, sine of 7 pi over 3, that's just going to be sine of pi over 3 is going to be equal to root 3 over 2. So, add a root 3 over 2. And distribute this 4. Let's add up like terms first, so cancel out these for pi. Then, minus 2 root 3 plus root 3 over 2. All multiplied by 4, so the final answer is going to be 4 pi minus 8 root 3 plus 2 root 3 equals 4 pi minus 6 root 3.
Okay, to give you guys an example of a BCFRQ problem, we have number 14. The graphs of the polar curves r equals 4 and r equals 3 plus 2 cosine theta are shown in the figure below. The curves intersect at theta equals pi over 3 and theta equals 5 pi over 3. Let r be the shaded region that is inside the graph of r equals 4, but outside the graph of r equals 3 plus 2 cosine theta. Write an expression involving the integral for the area of r. So, as you can see for this graph, we have the two intersection points. So this one's at pi thirds, so let's draw a line for that. This one's at 5 pi thirds, so let's draw a line for that. So we can see that the areas of the two functions are split up by the angles drawn are this thing and also this thing. So to find r, we want to subtract this greater area with and then the smaller area. So to do that, the following integral expression will be 1/2 integral pi thirds to 5 pi thirds of 4 squared, that's the for r equals 4, okay, minus 3 plus 2 cosine theta squared, that's the limison, and d theta. So that would be the expression to find the area of r. But another way you can do this is to realize that r equals 4 is just a circle with a radius of 4. So going back to the graph, we can see that the angles pi thirds and 5 pi thirds split up the circle into a 2/3 section and a 1/3 section. So the area of this 2/3 section, we can just use the normal formula for the area of a circle to calculate. So thus, a different way to express the area of r would be the following. 2/3 of the circle with area 16 pi, because 4 squared times pi, minus the integral, or 1/2 the integral, from pi thirds to 5 pi thirds of that one section in the limison. And thus we have that expression. And those two expressions are both ways you can represent the area of r.